Hi there. So today we're going to be talking about forward propagation in neural networks. So we're going to be exploring the intuition and math behind forward propagation, building off of simple matrix multiplications, and then trying to implement it in Python from scratch. So hopefully this helps you develop some intuition on how forward propagation works and how you might want to go on to approaching your own implementation of forward propagation in neural networks. So let's get started. Okay, so let's talk about forward propagation. So what is forward propagation to begin with? So when we talk about forward propagation in the context of neural networks, we're referring to the process of passing data through the neural network through all the weights, nodes, and biases and activation functions in order to arrive at a result. So this can either be for making predictions or during the training process, we use forward propagation to calculate loss so that we can later adjust the weights to arrive at a better result. So in this video, we're only going to be talking about the actual forward propagation process. Calculating loss and adjusting weights is the topic of another video. So just some prerequisites in order to get the most value out of this video. You should know basic linear algebra, just matrix and vector operations. This is important just to understand the intuition behind the math that we're going to be looking at. You should know a little bit about statistics. You should be familiar with NumPy and Python because we will be doing a bit of coding in this video. And you should have a basic understanding of what neural networks do and how they're structured. So that includes the weights, biases, activation functions, and how predictions are made. You don't need to understand exactly how they work. That's the point of this video, but you should have some experience with neural networks. Okay, so let's look at a basic neural network. So you've definitely seen this before, and we're just going to identify the different parts of the neural network so that we can look at how we can implement these on a lower level. So the first thing is the input layer. This is where our data is going to get passed through. And if you notice, this specific simple neural network has two input nodes or neurons. So that means that we're going to have two input features in whatever data we pass in. Now, this is intentional, and we're going to explore why in a later slide. And the next thing that we need to look at is the input weights. So these are the weights that are going to essentially transform the inputs into, I guess, the values of the next layer, so the hidden layer in the neural network. So this is a fully connected layer, meaning that every single node on the input layer is connected to every single node on the next hidden layer. And speaking of that, the hidden layer is the part of the neural network which carries values propagated from the previous layer. So in this neural network, we only have one hidden layer, but most neural networks have many, many hidden layers, especially deep neural networks, to make accurate predictions. And the last thing is our output neuron, which in this neural network we only have one, but we can have more than one. For example, in classification problems, we can have two to predict true or false results, or we can have multiple to classify multiple different results in neural networks. But to keep things simple, we only have one output neuron right now, which takes input from all the nodes in the hidden layer and uses that to make a prediction. Okay, so now that we've identified the parts of our neural network, we're going to be looking at the input layer and the input weights in the next slide to try and see if we can represent this in some way using matrices. So how do we implement this in code? Well, almost all operations in neural networks are conducted through matrix and vector operations. We can propagate data through the weights, biases, and activation functions of our network by storing it in a matrix. So we're going to try and implement the above network in code and using matrices with some fake weights to simulate the propagation of one data point, just because doing a whole data set would be incredibly time consuming. And we're going to try to do this to get a better understanding of what's actually going on under the hood. So let's get our data ready. So consider this data set of just 4 samples, and we have 2 features. So we have age and experience. And we also have one label. So label, it refers to what we're trying to predict. Now, we're not actually going to predict anything in this video just because we're not going to tune our weights to create a coherent result in any way, but I just included that there because that's most likely what your data is going to look like in a real world example. So we have two features, age and experience, and we have 4 rows. So we can represent this in a matrix such that each row in the matrix corresponds to one sample, and then each column in that matrix corresponds to the features of whatever data you're looking at. So in this case, we have 4 samples, so the amount of rows in our matrix is 4, and we have 2 features, meaning that we have 2 columns in our matrix. So we're going to use this in the next slide to try and perform some operations on it. So once again, looking at the rows and columns in our matrix, remember the matrix multiplication rule. This is going to come up a lot. So it's important that we have n rows. So in this case, 2 would be n, and k columns. So in this case 4 would be n because we have 4 samples, and k columns. So k in this context would be 2 because we have 2 features and therefore 2 columns. So these dimensions are important to remember, especially if you're designing a neural network from scratch, because you need to make sure that your matrices are the correct shape, or else multiplication won't be defined and you're just going to get an error, especially if you're using a library like NumPy. You really want to make sure that your matrices are in the correct shape if you want to actually get a result. So let's look back at this neural network and see if we can find a way to represent this in matrices. So we've already represented our fake data, and now let's see if we can take these weights and represent them in some way using a matrix. So we have our data on the right, on the left, and we have a set of 6 weights on the right. Now, right now, this doesn't look like it makes any sense. You might be wondering why the subscripts don't seem to go up in sequential order. Well, that's because the subscripts on the weights actually correspond to the neuron that they come from and the neuron that they're pointing to. So for some intuition, let's look at the first column. So these 2 weights over here in the first column are the weights that point to the first neuron. And the first subscript, so both of these have a subscript 1 as the first value. The first subscript corresponds to the first neuron. Now 1 and 2 simply mean that this first weight comes from the first neuron and points to the first neuron in the hidden layer. And then this second weight comes from the second neuron and then points to the first neuron in the hidden layer. And then and so on for these other columns. So this column would represent all the weights that point to this node in the neural network, and this column would represent all the weights that point to this neuron in the neural network. So the reason why we represent this in this specific shape is because we want to multiply these 2 matrices together. Now right now the weights aren't defined, but just as a placeholder I place W here. We're going to give this some fake weights later and actually perform a calculation. But if you want to understand what's actually going on when we multiply these matrices, so essentially if you remember matrix multiplication, we're going to multiply the first row by all 3 of these weights. So we're going to multiply, you can kind of think of this as a vector of length 2 with this column, and then we're going to find the dot product of that vector multiplication. And then we're going to do that with the second column and third column, and we should get 3 different numbers. Now these 3 different numbers, after we complete this multiplication, is going to correspond to the values of these 3 nodes. So that's why the amount of columns in our matrix is 3. The columns in your matrix that you're using for weights should always be equal to the number of neurons in the next layer that you're propagating towards. So we're going to look at this on the next slide and see how we would go about calculating them. And we're only going to look at the first sample for now. Now, in an actual neural network, you would multiply all of these at once, but for the sake of this video and to not overcomplicate things, we're only going to look at one sample. So we have the first sample here, and we have the weights, and I've color-coded them so that we can easily look at which calculation corresponds to the results down here. So we're going to find the dot product of this sample, and then the first column here And this is just going to be 23 times the first weight and then 2 times the second weight. So if you know how to find the dot product between two vectors, we're going to do an element-wise multiplication and then find the sum of those two products. And then we're going to repeat the same thing on the second column and the third column, and then we get these two results here. So if you think about it, these three numbers here, these are going to be scalar values or just floating point numbers, are going to correspond to the values that take place inside these neurons. So the blue value is going to go to the first neuron, the red is going to go to the second, and then the green is going to go to the third neuron. So also over here, the result is a 1 by 3 matrix. Now, it's important to remember the only reason we get one row here and not 4 is because we've only used the first sample in our data set. So we had 4 data points here, and just for intuition, had we used all 4 data points, we would have a 4 by 3 matrix. So we'd have 4 rows for which each column in those 4 rows would represent the values of the neuron for that specific feature. So we want to separate out these features just to show how each calculation works, because each of these features are each of these samples are independent of one another. So we don't really need to include them all when we're conducting calculations, but when you actually implement this in code, you're going to be calculating all of them at once. So now moving on to the next slide, or actually now we're going to try and code this in Python. But first we need to assign some fake weights here so that we actually get a real number when we multiply these matrices out. So on the next slide, I think I've initialized some weights here. Now these don't mean anything, but they're just some random decimal values. And you can try and calculate this by hand. In fact, I would encourage you to try and multiply this vector value with this matrix and see if you get the same result as when we do it in Python, because it would really help to understand the operations that are going on the lower level if you can try and get the same result doing it completely by hand and then using NumPy to help you out. But we're going to be making this matrix in Python and trying to evaluate this calculation so that we can further understand how the propagation is working. So I'm going to move on to Google Colab, and we're going to hopefully see how this multiplication turns out. Okay, so now that we have Google Colab open, we're actually going to try and implement the forward propagation in Python. So the first thing that we want to do is we're going to import our tools. So all we're going to need for this coding tutorial is just NumPy. So we're going to import NumPy as NP, and we're going to initialize the 2 matrices that we want to work with. So first we're going to initialize the actual sample. So this is just going to be equal to a NumPy array, and we want it to be 2 dimensions, but it's only going to have 1 sample, which is going to be 23 and 3, 2, and we're also going to initialize our layer 1 weights. So this is the weights that we were looking at previously, and this is going to be equal to a NumPy array, and the shape of this array is going to be as follows. So we're going to initialize a 2-dimensional matrix, and it's going to have the values. I'm just going to look at the slide. So we need 0.5. Let's see what else we have. Okay. And then the other row. Okay, and we're also going to initialize a function. This is just to show how activation functions would play into this. So we're going to use the rectified linear, or RelU, activation function, and we can just define that as def RelU. It's going to take in a matrix X, or any NumPy array, and it's just going to return numpy.where. So this is going to take a Boolean expression and apply it everywhere in the function. So we're going to check where x is greater than 0. So if you don't know, the rectified linear function just takes in some data and returns 0 if the data is negative, and returns the data value if it's positive. So it's essentially taking the maximum of 0 and that data point. So if x is greater than 0, we're just going to return x. Otherwise, we're going to return 0. So we're taking the maximum. And what we're going to do now is the result is going to be equal to ReLU of the NumPy dot function. So we're taking the dot product of this vector and this matrix, or just the proper matrix multiplication of these two matrices, but we're just going to use the np.dot function for that. And we're going to pass in sample and the layer 1 weights. Yeah. Okay, and then we can just print result, and hopefully I didn't do anything wrong, and this should give us the result. So it's just going to import NumPy, and it should, right, so this should be the same result that you would get if you were to do this calculation by hand. Once again, I encourage you to try it. It's quite a simple operation, shouldn't be too many calculations, and now we're going to move back on to the presentation and try to implement the second layer, because this is only the output of the first hidden layer, and now we also need to propagate this output to the final output neuron before we can predict a result. In this case, the result doesn't really mean anything because all these weights are fake, but in a real neural network, that's the next step that would follow after this. So now that we've completed the first matrix multiplication, we now have 3 values for each of our neurons. And if you want to recap, we got these 3 values simply by multiplying the weights matrix by the first sample. Now we're only working with one sample here to keep things simple, but now the next step that we have to do is to take the values in the hidden layer and propagate them further into the single output neuron. So in this network, just to keep things simple, I only decided to include one output neuron, but neural networks can have 2 or as many output neurons as you want, depending on what you're trying to predict. Multiple neurons are usually good for classification. For example, you can have 2 neurons if you want to classify something as true or false, and the value of those 2 neurons can be your confidence for each result. But for now, we're only going to include 1 neuron in the output layer. But then that raises a question: what matrix do we multiply these 3 values in order to only get 1 value in the end? So to answer this question, you have to think about the matrix multiplication rule. So if you look back at the shape of our results in the second layer, we have a 1 by 3 matrix, meaning we have 1 row and 3 values. So if we multiply this 1 by 3 matrix by another matrix and we want a scalar result, a 1 by 1 result, the second dimension of that matrix also has to be 1. And in order for matrix multiplication to be defined, the first dimension, or the number of rows in that matrix, should be equal to the number of columns in this matrix. Therefore, we should multiply this 1 by 3 matrix by a 3 by 1 matrix. And we're going to do that on the next slide. And of course here, we're just looking at the output layer, and we're going to use this to make a prediction. But the actual weights takes a different shape than last time. So instead of having 6 weights in a 2 by 3 matrix, we have 3 weights in a 3 by 1 matrix, or you can call it a vector of length 3. So I've color-coded the values that are going to be multiplied together in the dot product of these 2 vectors, you could call it, to get this single scalar result. So we're going to multiply these 3 floating point values with each of the corresponding weights. Now I want you to look at the subscript of each of these weights. They all have the first subscript of 1. This is because we only have 1 neuron in this layer. And they have subscripts ranging from 1 to 3 in the second index. That's because we have 3 neurons in the previous layer. So each of these subscripts denote the origin of the weight that they represent. So now that these 3 values are going to be multiplied by each of these weights in order to produce this single scalar value. And we're going to explore how we can do this in Python as well. So after assigning some fake weights to this a set of weights as we did before, we can get a single scalar result. So if you want, you can pause the video and try to conduct this dot product calculation on your own. You just have to multiply the corresponding components of each of these vectors, and you should get this scalar value. Now note, again, we're only working with one sample. Usually, when we work with multiple samples, we would get a vector of scalar values where the number of columns is 1 and the number of rows is n, where n refers to the number of samples that you have in your data. Because, in neural networks, you want to multiply all your data and propagate it at once, because it's just a lot faster to do it that way. But again, for this tutorial, it's more easy to understand when we're only working with one sample at a time. So that's why we only have a single result. So we're going to explore this in Python again, and then we're going to return back to the math. Okay, now we can try actually coding the output layer along with its weights and trying to get the same result that we saw in these slides from the result that we have over here. So I'm going to create a new cell in Colab, and I'm going to set the layer 2 weights, or I can just call these the output weights. And this is going to be equal to a new NumPy array. And since it's still a two-dimensional matrix, we want to pass in a first array object, and then each element in this array, I don't know why it's doing this, is going to be a list. So we have 3 values. So I'm just going to look over here and see what weights I need to put in. So okay, now we're going to multiply these weights using the same numpy.dot function, but we're going to multiply this with the result. So we're going to pass in the output of the previous layer into this new layer, you can call it, and then we're going to see what result we get. So we already have this result variable defined. I'm just going to run this cell again, and we're going to print. We're not going to call the rectified linear function this time, just because we want to we're probably not going to use rectified linear on the output neuron. More often you use sigmoid, but I'm not going to use any activation function this time, just because it's not really relevant to what we're looking at right now. So sorry, np.dot, and we're going to call result. We're going to pass in result as the first argument, and then what we're going to multiply it with is the output weights. And I think, yeah, this should work, and let's see. Okay, so we get the exact same scalar value. Obviously, it's not in a floating point form. We need to reduce some of the dimensionality, just because when you multiply matrices in NumPy, it usually likes to return the same number of dimensions as you put in. But we have the exact same value that we looked at in the PowerPoint. So this is going to be your prediction, and if you want, you can pass this into a sigmoid or whatever activation function that you want, but in a neural network, this would be your final result. And again, this is only for one neuron. If you had more than one neuron, you would have more than one row here, and again, this is also for only one sample. So if you had more than one sample, you would have more rows going below this. And sorry, if you had more neurons, you would have more columns, just to represent the values of each neuron in the final layer, just like you have here. So yeah, that's about it for the output layer. So later we're going to try and incorporate all of this into a single function called feed forward, and we're going to try and look at some patterns between the shapes of each layer's matrices, so that hopefully we can gather some intuition as to how the values transform from layer to layer. So we're going to go back to these slides now. Okay, so now that we have the output from our output layer, we can represent this entire neural network as a set of weights inside these matrices. So if you notice, looking at the shapes of all the matrices here, the number of rows is always preserved throughout these calculations, whereas the number of columns changes depending on the layer that we're in. And the number of columns, of course, corresponds to the number of neurons of the layer that we're in. So if you can see, depending on the size of our input, so for example, we have 4 rows here, we also have 4 rows in the output. Now the reason that you didn't see this when we were doing our calculations in Python or in the previous slides is because we only worked with this first sample, and as you can see, this was the result of all of these weights applied to this first sample. And then these next values are just if we were to apply those calculations to these following samples, and you can test this out in NumPy if you'd like with the previous weights that we mentioned. We're going to explore how the entire model can be implemented in Python, and we're going to be looking at how the shape of the matrix result, so the shape of the calculation changes throughout each layer of the neural network, and you're going to kind of see how the output shape of one layer becomes the input shape of the next layer, at least when you're concerned with the number of columns or rows, depending on which layer you're currently working on. So we're going to try doing that in Python to gain further intuition, and we're going to design a function, hopefully, that can take in a set of data like this, specify the number of neurons in the hidden layer and the input layer, and conduct a similar calculation like this, but all in one go without having to get out the output like we did before. So we're going to move on to coding now, and hopefully you can see how the shapes of these matrices tie into the neural network graphic that we looked at before. Now we're back to coding, and we're actually not going to use any of this previous code except for this activation function and obviously NumPy. But what we're going to do now, I'm going to delete this cell here, and I'm also going to delete all this code, is we're going to define a forward function, feed forward function. It's going to take in x, and it's also going to take in 2 arguments. So it's going to take the arguments of the input layer, the hidden layer, and we're actually going to add in another hidden layer. So we're going to have an input layer and 2 hidden layers, and then it's going to, once again, propagate to one output. So in fact, we don't even need to specify the input layer's shape because that's going to be known already from the shape of x. So we're going to pass in 2 parameters, so hidden layer 1 shape, or we can just pass in hidden layer 1, and we're also going to do hidden layer 2. Okay, and these are just going to be 2 integer values, which tell us how many neurons we want in each layer. So I don't know why it's not showing types here, but I think that's valid. So what we're going to do is we're going to initialize 2 sets of weights, or 3 sets of weights first, actually. So the first set of weights is going to be the input weights. So that's going to be what's going to propagate the input to the first hidden layer. So the shape of these weights is actually just going to be, okay, so we're going to get the shape of x. So rows and columns is going to be equal to x dot shape. Okay? And so now that we have the rows and the columns, we have to think back to the matrix multiplication rule. So the first dimension of the input layer should be the number of columns that x has. So we're actually going to just initialize some random weights. So input weights is going to be equal to numpy.random.rand. So this is just going to generate a matrix with some random values, some random floating point values, and we can specify the dimensions that we want. So the first dimension, the number of rows, is going to be equal to the number of columns of the input. Okay, so we can just put cols here. And then what should the number of columns in this matrix be? Well, we know that the layer that we're going to pass this data to after is going to be hidden layer 1. And in order for matrix multiplication to be defined, we need the number of rows in this matrix to be equal to the number of columns in hidden layer 1. We need the number of columns in this matrix to be equal to the number of rows in hidden layer 1 because we're going to be multiplying these matrices together after we get that result. So the second argument for the shape of input weights is going to be hidden layer 1. Hidden layer 1, and again, this is just an integer value to tell us how many neurons we want. So we have our input weights, and now we can initialize hidden layer 1. So I'm just going to call this HL1. Okay, stands for hidden layer just because I don't want to override this variable that I already declared. And this is going to be equal to, again, numpy.random.rand. But what shape is this going to be? Okay, well, this is going to be, remember, hidden layer 1, we've already specified what shape the rows should be, or how many rows we should have. So this is just going to be hidden layer 1 rows, or however many rows we specify. And how many columns should this have? Well, if you think back to what we did for input weights, the number of columns of the matrix should be equal to the number of rows in the matrix that we're going to pass the results to after it. So the next layer is hidden layer 2. So actually the number of rows the number of columns in this matrix in hidden layer 1 should be equal to the number of rows in hidden layer 2. And hopefully you can sense a pattern here that the shapes of each matrix is dependent on not only the previous but also the next layer in the neural network. Okay, and now hidden layer 2. So hidden layer 2, again, you should be able to notice a pattern here, is going to be equal to numpy.random.rand. And again, we're going to pass in the second dimension from the previous matrix as the first dimension here. And now, remember I mentioned how we're going to have an input neuron that's only, we're going to have an input layer with only one neuron. Okay, so that means that the second dimension, the number of columns inside the second hidden layer, which is the final hidden layer, should be 1 because we only have one output. So we can just pass in 1 here. And if you wanted to make the number of output neurons variable, you could also just pass that in here. In fact, let's do that. We can just call this output shape. And then we're going to pass in an output shape here. And this is also going to be an integer value. So we have our row, we have our input weights, and then we have 2 hidden layers. And now we can just carry on with our feed forward operation. So how are we going to do that? Well, it's pretty simple. We're going to multiply x with all of these matrices sequentially. So we're going to take the output of one multiplication and plug it into the other hidden layer and do that multiplication, and then repeat that again until we get to the output. So the way we're going to implement that in code is we can set out equals, or yeah, we can just set output equals to numpy.dot, and then we're going to pass in x, which is going to be our data, and then we're going to pass in the first layer, which is the input weights layer. So input weights. Okay, and then we're going to actually apply the ReLU function, the rectified linear function. So output is going to equal to whatever the rectified linear function gives out, which is just going to be the max of all these values and n0. So it's going to be equal to ReLU and then the previous output. So we're going to override this variable again. And then actually what we're going to do here, I'm just going to copy this line. And then the output again is going to be equal, the output again is going to be equal to the hidden layer 1, so HL-1 times x, or times the previous output, sorry. We don't want to multiply it by x because x is just our old data variable. We want to pass in the previous output from this layer into the next layer. And again, output is going to be equal to the rectified linear function of that output. And then we're going to repeat this process with hidden layer 2. And as you can see a pattern here, we're plugging in the output into our layers. And then we're going to perform the rectified linear function again. And actually, no, we don't need to do that because this is going to be our final result. This is going to return a scalar or whatever our output shape is, but I am going to specify 1 just when we're testing it. And after this, we could do like a sigmoid function, but I'm not going to define that here. So we're going to see what result we get. Okay, so let's test this function out. So I'm going to just make some fake data. So our x is going to be a NumPy array. And actually I could generate some random data here, but I want to get some clean numbers. So I'm just going to do like 1, 2, 3. Or actually I should choose some more random numbers, but who cares for now? Okay, So we have, I guess, a 3 by 3 matrix, and it doesn't matter what shape the data is in or how many samples we have. We could even add another layer because the shape of the input layer is going to be dependent on whatever our shape of X is. So we don't really have to worry about what type of data we pass in to here. So we're going to try and get the result of whatever this forward function is going to return on X. So we're going to pass in X, and the hidden layer 1, let's say we want 4 neurons in this. We want 4 neurons in hidden layer 1, and then hidden layer 2, let's say we want 6 neurons in this. And let's say our output layer, or no, the output shape is going to be equal to just 1 for now. We only want 1 neuron. And just for intuition, what we're going to do is we're actually going to print the shape of all of these matrices, so hopefully you can understand what's going on under the hood. So I'm just going to print so we're going to print actually no, we're going to print hl dash or underscore 1 dot shape, and I'm going to do that for hidden layer 2 as well. And I'm also going to do that for the input layer. Input weights dot shape. So I think this should be free of any errors. I'm just going to copy this and I'm going to print whatever. Oh, okay, whatever. I'm just going to print whatever result we get from this, and let's see what we get. So I'm going to run this code cell, and okay. Oh, I forgot to return. Mistake. So I have to return this output, and we get, okay, so the output shape, let's see, our input shape is 3 and 4. Notice how 4, the second dimension here, gets passed in here as the first dimension of the first layer, and the second dimension here also is passed in here. We get this from our parameters that we defined, and again, the final layer shape gets passed in here from our parameters. Okay, so if we look at the shape of the input, so it's a matrix with 3 rows and 4 columns. Now the reason we have 3 rows in our input is because we have 3 columns in our X input. So the input weights have to have 3 rows in order to multiply nicely with the X input that we pass in. And then, of course, and then similarly, we have 3 rows in the hidden layer, just like we have 4 columns in the input. And you can see this pattern passed on along here, just so matrix multiplication is defined. So you can see as we pass in the output from one layer into the input of the other layer, we kind of have certain dimensions preserved. And if you notice, the 4 rows that we passed here have been preserved throughout all the multiplications, because this was a 4 by 3 matrix. So throughout all of these matrix multiplications, the dimension of 4, the number of rows, is going to be preserved even in the result. So we get this result over here from all of these weights. So we get a 4 by 1 result, obviously 1, because we specified the output shape of 1. If we were to specify this as like the output shape of 2, we get two columns where each column would correspond to, if you want to think about it intuitively, the value of a neuron in the output layer. But again, in the diagram that I showed before, we only had 1 neuron, so you could think of this as the value or the result of propagating each of these data points, because you can think of each of these rows as a different data point. So hopefully that helped you understand some of the intuition behind how you can implement the forward propagation function of neural networks into actual code, because the diagrams and the intuition of neural networks as they are usually represented can be a bit difficult to understand, especially when you want to implement them as something that can be calculated with matrices. So hopefully this sort of helped your understanding of how neural networks are implemented on the lower level. So that just about concludes the video. Thanks for watching, and I'm gonna hopefully try to make some more videos on neural networks soon. I'm going to try to see if I can make something on backpropagation that would really tie into this video very well. So stay tuned for that.